Hello everyone, welcome to Chapter 1, Logic and Proofs of the Discrete Mathematics textbook. I'm going to be loosely following the textbook for some like the structure and pacing of the course. I will deviate from it in some areas, but just to keep things consistent and so that you can refer to the textbook if you need to, I will label it with like the chapter and like the subsection that we'll be in. So today, we're starting off with Chapter 1, Section 1.1, so we're talking about propositional logic. CSC 248 is probably best described as an applied logic course, but in order to apply the logic, we need to actually develop the logic first. So that's going to be our goal for the first few weeks, especially. So when we're doing logic, we're often doing logic linguistically. So our first step is we want to make language precise, because logic is a very precise thing and language is a very unprecise thing. So we want to take language and sort of pare it down so that it can be used in a very like quantitative way. And so we're going to need to sort of break it into its constituent pieces. And the smallest piece of logic that we're going to be dealing with, or the smallest piece of language that we're going to be dealing with to develop logic, is called a proposition. So definition. A proposition is a declarative statement that is either true or false, but not both. Okay, so there's a couple different important pieces to this idea. The fact that it's a declarative statement, so you can't have a question or anything. And the other important piece is that it's either true or false. So it's like its truth value is unambiguous. So for example, if we had something like, it is raining outside, this is in fact a proposition, because it's a declarative statement, it's declaring something, and it is either true or false. Either it's raining outside or it isn't. There's not really any ambiguity to it. But maybe something like what time is it? This is not a proposition, because for one thing, it's a question. It's not even a declarative statement. But for another, it has no truth value. There doesn't make sense to say, is it true what time it is? No, that doesn't make any sense. So this is not a proposition. Maybe something like 2 plus 1 equals 37. This is a declarative statement. We're declaring that 2 plus 1 is equal to 37. This is a proposition, because it's declarative, as I just said, and it's false. So it is either true or false. And maybe lastly, if we have something like x plus 1 equals 2, for example. This one's a little tricky, because you think, oh, it's an equation, so it's probably either true or false. But the problem is we don't know if it's true or false, because we don't know what x is. And we're going to get some tools to deal with things like this in the future section. But for now, this, because we can't decide its truth value, is not a proposition. Okay, so there's some examples. Usually, instead of writing out the entire statement when we're dealing with propositions, we use propositional variables. So we can represent propositions with propositional variables. I cannot spell to save my life, so if you see me pause in the middle of writing a word, it's because I'm trying to think what the order of the letters is. I trust that you can spell, so you'll probably see me make a spelling mistake, but just know that I can do math, I just can't do words. Okay, so for example, P and Q are pretty common choices of propositional variable for propositions. I think your book uses lowercase. I personally prefer uppercase, so I might say something like P and then like a colon to denote what it's going to be, and I'll say like this apple is yellow, for example. That would be a proposition because the apple is yellow or it's not. Okay. Now, just propositions on their own are not very interesting. They're great little tiny building blocks, but we need mortar, I suppose, to actually put the bricks together. And that is where logical operators come from. So we can make what are called compound propositions. So I'm usually going to refer to these as statements. Just kind of a little bit of a shorter name for them, using logical operators. Okay, so here are those operators. So they all have a sort of symbol attached to them, and then a sort of name, and then like an English equivalent of, you know, what it is it's trying to represent. Because, again, we're trying to make language precise, and to do that, we need to worry about what language is doing. So the first one is a squiggle, and its name is negation. Some people also write it as like a kind of a bar like that. I prefer the squiggle personally, but either works. This is not. So negation, not. You say something like, the car is red, and you wanted to negate that, you'd say the car is not red. So there's negation. We also have this sort of upside down V shape. This is called conjunction. And its job is to represent the idea of and. And then similarly, if you flip it over and you got that V shape, this is going to be disjunction. And this is going to be representing or. Very important that this or is inclusive. Just like it's convention, like mathematical convention, that when we use or in mathematics, we mean inclusive or. And in the cases where we specifically want exclusive or, we just say that, we say exclusively or, but not both, or something like that. But in general, if you just see or, it means inclusive or. The next one is this kind of arrow with double bars like this. This is a conditional, which some people see in K-12 education. It's representing statements that look like if, then. So like, if it is raining, then I am wet. That would be a conditional. It's also read as implies. Okay. There's one more that your book mentions, and I'll mention so that you kind of know what it is they're talking about. It's the exclusive or. And so, yeah, this would be or exclusive. Exclusive or is not very commonly used in mathematics and in proofs, and that's the kind of thing we're trying to develop to apply to algorithms and the sort of computer science that you're interested in. So we're not going to be using exclusive or really at all, but I'm just kind of showing it to you so you're exposed to it and it doesn't surprise you if you do run into it at some point. In general, we're going to be using inclusive or. All right, so there's our sort of connectors. So let's see what happens when we put some pieces together. For example, let's let our propositional variable P be it is raining outside. And then we'll have Q be I have an umbrella. And we'll let R be I am soaked. Okay, so all of these are indeed propositions because they're all declarative statements. They're declaring something, and they are all either true or false, but not both, right? Either it's raining or it's not. Either I have an umbrella or I don't. Either I'm soaked or I'm dry. All right, So let's see what happens when we combine some of these with some of these new symbols that we've got. So if we do like P, V, Q, so P or Q, we're going to translate this into an English statement just to kind of see exactly how this shakes out. I could say it, since P is it is raining outside, so we're going to go it is raining outside. And then we got the or right here, or, and then Q says I have an umbrella, or I have an umbrella. Okay. Maybe we do something like this. Maybe we do R implies P. Okay. So R says I am soaked. So remember this conditional is if dot 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 then dot dot dot. So it's going to go if I am soaked. Then, okay, and then we've got our P, which is it is raining outside. So then it is raining outside. Okay. But we can make even bigger ones. Let's say, for example, we're going to do something like P and Q implies not R. So there's a couple different things going on in this one. So usually when you're trying to translate these things into English, the if-then, the conditional is like the first main thing that you're going to want to worry about. So we really should read like this as, if P and Q, then not R. So we want to do if, and then P and Q. So P is it is raining outside. So if it is raining outside. And then we get and Q. So and I have an umbrella. All right, so we did if P and Q, and then we have to do then, not R. So R says I am soaked. Not R would be I am not soaked. Cool. So translating symbolic logic into English sentences is a pretty good skill to get you comfortable with what exactly these things are trying to represent. Oftentimes, we're also going to be very interested in taking an English sentence and translating it back into propositional logic, because sometimes it's easier to manipulate things logically when we write it down in the propositional logic symbols. So, unfortunately, going the other way is a little trickier. But it's one of those things that gets easier the more you practice it, because you kind of see like what are the key sort of phrases and structures in the sentences that you need to key into and pull out. So let's do some practice together. Let's say I have an umbrella and I'm still soaked. Okay, so remember up here we've got these English equivalences. So those are going to be important in this. We're going to be looking for these sort of like key words or these key sort of phrases in these sentences to kind of pick apart exactly what the structure is. So if we kind of look at our sentence here and we see if we can pick any of those out. Let's see, I have an umbrella and I'm still soaked. So I see that we've got an and there. So it looks like that's sort of a logical operator, and it looks like we've got two pieces. I have an umbrella. That looks like a declarative statement, so that's probably going to be one of our propositional, just propositions. And I'm still soaked is also a proposition, so it looks like that's kind of the basic structure here. So I have an umbrella. I think that was one of our P, Q, or R. Yeah, so that's going to be Q. So we have Q, and then the and is going to be that upside down V shape, and then I'm still soaked. The closest thing we have is I am soaked, but I am soaked and I'm still soaked mean is virtually the same thing. So in this case, it's going to be our R. So this is Q and R. Okay, let's do another one. Maybe one that maybe is a little less straightforward. So let's do if it's raining outside, and I don't have an umbrella, then I am soaked. Okay, so we want to try to translate this into symbolic logic. The very first thing I notice is that we have an if-then structure. So that's going to be very important in sort of deciding what it is, or like how this thing is built. Then I'm going to look for any other key phrases. I see an and there, so let's go ahead and note that there's an and there. So if it's raining outside, so it's raining outside looks like it's a proposition, so that's pretty good. And then and I don't have an umbrella. So I don't have an umbrella, that's also a proposition. And then we've got the then, and then I am soaked. So there's our other proposition. Okay, so we're going to have a conditional here. So the conditional has two pieces. It has the first bit, our hypothesis, and the second bit, our conclusion. So the hypothesis is the part in between the if and the then. So it looks like it is raining outside, and I don't have an umbrella, so that's going to be our hypothesis. So it's raining outside, that was our P. And then we have an and, so we have that right there. And then I don't have an umbrella. Well, if we look back at our statements here, Q is I have an umbrella. And I don't have an umbrella is going to be its negation. So we need not Q. So we have P and not Q here. Okay, that's from the don't right here. That gets us our not. Okay, and then so we've got this is our hypothesis. And then we've got then I am soaked. And I think that's just going to be our R again. Cool. All right. So now that we have propositional statements and we've got our logical operators, we want to analyze the truth value of these propositions, especially when they're a little bit bigger. To do that, we use truth tables. Okay, so for example, like the smallest possible truth table we can do is just with one propositional variable. So what we do is we have a column for each of the propositional variables and then a column for the thing we're trying to analyze. So if we just have one propositional variable, we just kind of fill in here true and false. It's all the different truth values that this thing can have. It's a proposition, so it can only have two, true or false. And then maybe we're interested in what not P would look like. Well, not P is going to be, if P is true, then not P is going to be false. So we get an F there for false. And if P is false, then not P is going to be true. So negation sort of flips the truth value of our proposition. Okay, let's kind of do maybe something a little more interesting with the other logical operators. Let's kind of look at what if we have P, Q, and what happens if we do P and Q. Okay, so now we need to do all the combinations of the truth values of P and Q. So maybe P can be true and Q can be true. Maybe P is true and Q is false. And then we do false, true, and false, false. And I think that's going to be all the combinations of truth values of our two propositional variables. Okay, so what AND does is AND wants both of them to be true at the same time. If one of them is false, deals off the AND is false as well. So if P is true and Q is true, then P and Q is going to be true. But for all the others, so like for the next one, we've got P is true and Q is false. Since Q is false here, this thing right here, the AND is going to end up being false because AND is very picky and it wants both of them to be true at the same time if it's going to be true. The same issue on the next line, except now P is false here, so this is going to be false. And they're both false in the last line, so AND is definitely going to be false as well. Okay, so this is not and this is AND. And let's go ahead and do the other sort of basic logical operators. So if we do P, Q, and if we look at P or Q, its truth table looks a little bit different. So or says, because we're doing inclusive OR, as long as one of P or Q is true, the P or Q is going to be true. So for this top line, P is true and Q is true. They're both true. So P or Q, it definitely has something that's true in it, so it's going to get true. All right. If P is true and Q is false in this line right here, P is true, and that right there is enough to make P or Q true, even though Q is false. So this is still going to be true. And then the same thing kind of happens down here in this line, because Q is true, even though P is false. We've got one true, and that's enough to make P or Q true. So this is also going to be true. But then in the last line, they're both false. So you're going to get false or false. So we're going to get a false out. Okay, one last one. P, Q. This one's arguably one of the more, or they're all important, but this one's probably the most important test. The conditional is interesting. The way to think about a conditional in terms of the truth values is a conditional is like a promise. So if you promise P is true, then your conclusion better be true. So P is like your promise, and Q is like you following up on your promise, is one way to think about it. So if you promise true and you deliver true, your conditional is good to go and it's true. So like, if it's raining outside, then I am wet. Imagine it is raining and I am in fact wet, then the conditional is true. On the other hand, if we make our promise and then we break it, so if we have P true and Q is false, then the promise is broken and this conditional is false. So for example, if it is raining outside, then I am wet. If it is raining outside and I happen to be dry at the time, so then P would be true, it is raining, but Q would be false, I am wet, I'm not. Then this conditional would be false, so that gets the F. But for the other two lines, we have our promise in some ways is false. Our hypothesis is false. And the thing about conditionals is that if the hypothesis is false, the conditional is automatically true, just kind of by convention. So that's what the truth table for if-then looks like. Okay. There's one more symbol that pops up a bunch, and I'm just going to address it now so we know kind of what it is. It's really the combination of two different things, but let's break it down. A biconditional is P if and only if Q. Symbolically, what this looks like usually is P, and then you have an arrow going both ways, Q, like this. And it's defined as P implies Q and Q implies P. So it's a conditional going both ways, hence the name, biconditional. Let's look at a truth table for this, kind of see what's going on here. So we'll do if P then Q, we'll do if Q then P, and then we'll use that to build P if and only if Q. All right. Get all our different ways we can combine. Okay. So we just did if P then Q. It's going to be true, false, true, true. So the promise was made and the promise was kept, true. The promise is made, the promise is broken, false. And then the hypothesis, the promise never was made, it is trivially true for those last two. Okay. And then the others, it's the same thing, just kind of flip the roles of P and Q. So Q implies P, we have true and true, so that's going to be true. And then Q implies P, we have false implies true. So the hypothesis is false here, we're trivially true. And then this next line we have true implies false, so that's going to give us a false. And then we've got false hypothesis, so automatically we're trivially true. Okay, since we're doing if P then Q and if Q then P, and we're using an and, we're going to require that if this is true, both of these must be true. And for this first line, that does in fact hold. So we have true and true, so we're going to get a true here. And then for the next one, we have like a false and a true, so like this is false and this is true. We've got a false in the and. The and is very picky. It does not like that, so we're going to get false out. And then I think the same issue pops up in the next line when we have true and false, so that's still going to be false because the and doesn't like that F in there. And then the last one has true and true. And says that's okay, and so we get it true. So here's the thing to note about the biconditional, is that it's true when the values of P and Q match up. So what this is saying, a biconditional really kind of links two propositions together, right? It says you're never going to have P without Q, and you're never going to have Q without P. So if P and Q are both true, then the biconditional is true. If they're both false, then the biconditional is true. The biconditional just says that these two things are going to match up everywhere. Okay, so now that we've kind of seen these logical operators, we can make larger truth tables for things. So we're going to end this section by doing some more examples. So let's say we wanted to do something like, let's do P, Q, and then I want to eventually analyze something bigger, so I'm going to make a few columns. Eventually I want to do a truth table for P, and P implies Q implies Q. Okay, so this one's kind of funky and big, but you see I've left some space for myself. That's because it's sometimes nice when you're analyzing large propositions like this to sort of break them up into constituent pieces. So, for example, like if P then Q might be a good piece to analyze. And then once we've got that piece, it might be nice to then figure out, sorry, I think I've got my parentheses in the wrong spot. There we go, that's better. It might be nice to then analyze P implies Q implies Q. And then from there we can do P and this thing right here. So breaking up into smaller pieces. Okay. Kind of fill in our truth values for our propositional variables, and let's go. All right, we just did P implies Q, so remember this can be true, false, true, true. All right, and so now what we have is we're going to take this, and that's going to be our hypothesis, and then that's going to be implies Q. Okay, so we get true implies true, so that's going to be true, okay. And then we get false implies false, so that's going to be true, trivially true. And then we've got true implies true, okay, so that's going to be true. And then, oops, come on. And then lastly, true implies false. We made a promise and it was broken, so that's going to be false. Okay. And so then our last step that we got to do here is we do this thing that we just did and P. So we want both P and this thing, or whichever row we're looking at, to also be true. We want them both to be true. So in this first top row, we've got, oops, that's not what I meant to do. We've got true and true, so that's going to be true. Okay. For this next row, we've got true and true, so that's also true. And then we've got false and true, so that's going to be false. And then lastly, false and false, that gets us false. Okay. Let's do one last example with maybe something a little bit bigger. Let's say we wanted to do something with 3 propositional variables, so P, Q, and R. So we got 3 things that we're playing around with here, and eventually I want to analyze something of the form. I want to do P implies not R, and Q implies not R. So maybe something like this is what we're interested in. So I'm going to break this up into some pieces. I'm going to do this piece and this piece separately, and then I'm going to conjoin them with the and. So I'll do P implies not R, and then Q implies not R. And then I'll add them together with the and. Okay. To fill out this, we need all the different combinations of truth values for P, Q, and R. So maybe true, 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 then true, true, false. And we get true, false, true, true, false, false. Okay, so I think that's all the cases where P is true. So now if we do false, true, true, false, true, false, false, true. Oh no, this should be a false. True, and then false, false, false. Okay. Bunch of different rows. Okay, so let's go ahead and do this. So P implies not R. So remember, not R, and you can make a separate column for the not R if you wanted. That's totally fine, just to make it really clear what's going on. But remember, it's just going to flip all the truth values here. In fact, actually, it might be a good idea to write that down. Let me make some room for myself. Ah. Not R. Okay, so if we look at not R, we're just going to go ahead and flip all the truth values. So we're going to get false, true, false, true, false, true, false, and true. Okay, so now we can go ahead and do this conditional. If P true implies not R, which is false, so that's going to be false. We broke our promise. And then we've got true and true, so that's going to be true. And then we've got true and false again, so that's going to be false. True and true gets us true. And then the rest, P is all false, so our hypothesis is false. So all of these are going to be trivially true from all of these F's right there. Okay? And we do the same thing with Q, same sort of procedure. This time we're just looking at the Q column instead. We've got true implies false, so that's going to be false again. True implies true, so that's true. False implies false, that's true. And then Q, false implies true. Hypothesis is false, so trivially true. And then we get true implies false. Our promise is broken, so that's going to be false. And then we've got true implies true. That works out. And then false and false for Q here. The hypothesis is false, so this is going to be trivially true no matter what not R is. Okay. All right, so now we're going to combine these together with our and. So we just do these two columns, and we and them together to get this thing right here. Okay, so we do false and false. Well, that's going to be false. They need to both be true for this to be true. But the next line actually has that, so that's going to be true. And then this one has a false in it, so false. And then true and true, so true. True and false gives us false. And then all these three are all true, because we all have truths there. Okay, cool. So that's how we make a truth table for larger propositional statements. This is going to be something that's going to help us develop our logic formally, and in particular when we start doing propositions and proofs, we're going to be using sort of these truth tables and the results that we get from them to make rules of inference and to say, like, what implies what, and like, if this is true, then what does that mean about this other thing? So that's why we're doing this, to sort of formalize all of that, and we're going to do some more advanced propositional stuff with quantifiers and some variables later down the line. Thank you for listening.